All right, so this week in the parent class, we're talking about optimization problems. And optimization problems really just reuse a lot of the material that we've already covered in Chapter 3, in particular finding maximum and minimum values. The difference is that we're applying them to word problems pretty much exclusively. So when I was looking over the material for the parent class this week, I kind of determined that there's not any specific prerequisite skills that we should focus on that we haven't already focused on. That's typically what we're looking at when we're covering this Maths 40 stuff, is what prerequisite material would best support what we're doing in the parent class that week. But because there's nothing specific that came up when I was thinking about it, I decided that this would be a good week to do some additional practice with differentiation, derivatives, right? And what I want to do is I'm just going to do 4 examples, and none of them are anything new to you. It's derivatives of functions, and we've seen plenty of this in the parent class. However, a couple of these problems are going to be more easily solved if we do some algebra on the function first to simplify it. Not all 4 of them, and not even the first one, but you'll see I'll mention it when we get to them. Some of these examples, if we kind of change the look of the function by manipulating it algebraically a little bit first, we're going to have an easier time with it. Let me start with this first one. Okay, f of x, which I forgot to write first, so it's on the right side like you wouldn't normally see it, but f of x is equal to the quantity 4x minus 3.5x squared all to the power of 13. Okay, so this is where you want to reach into your tool belt and figure out which of the various different differentiation rules would make the most sense here. And in this case, it's the chain rule. Remember, the chain rule works for composite functions. If I have one function sitting inside another function, I can apply the chain rule. A little bit more specifically, we have these different special cases of the chain rule, and this is the one that we would call the generalized power rule, because I have a function to a power. Without the chain rule, your only real option here would be to expand this out. But expanding a binomial to the 13th power is a nightmare. It's an absolute nightmare algebraically, and it's not at all what you want to be doing for a problem like this. So the generalized power rule basically just says this. I treat this thing like a power function, and I apply the power rule to it, so the 13 comes down. And then I take the original function that I had raised to a power, 4x minus 3.5x squared, but the exponent is now decreased by 1. So that's like what the power rule would normally look like. But then because this is really an application of the chain rule, there's an additional factor that comes out. I have to multiply by the derivative of this function out here. And the derivative of that would look like 4 minus 3.5x squared. The 2 will come down and multiply to the 3.5, giving me 7x, okay? And this is as simplified as I want it to be. I don't want to do anything else to it. So this is kind of a one-step problem if you know what to do, right? And hopefully we have now had enough practice with the chain rule that you can kind of see what those steps were before I did them. You know, you can predict them. Okay. Number 2. So this is going to be the first example where manipulating this function algebraically is going to save us a lot of effort. Because if I were to take the derivative of this as is, I have the natural log of a quotient of functions. And so this would require 2 things. It would require me to use the chain rule because I have a function sitting inside another function. And then in the process of doing that chain rule, I would also have to end up taking the derivative of the function on the inside, which would call for the quotient rule. And remember, the quotient rule is a bit of a messy one. So here's what I'm going to do instead. I'm going to use some algebra. In particular, I'm going to use some logarithm properties to change the way that this looks. So for one thing, I know that if I have the log of any type of a quotient, I can write that as the log of the numerator minus the log of the denominator. Okay? That's something that I know I can do from algebra. Next, what else can I do? Well, this term this factor right here, or not factor, but this guy, this natural log of x squared plus 1, that is actually as simplified as I can get that, because I don't have logarithm properties that tell me what to do when I have a log of a sum of two things. I can only deal with logs of quotients or products and simplify those. But I do have a product right here, 4 times e to the x. So this I can write as the natural log of 4 plus the natural log of e to the x. And then I still have this minus natural log of x squared plus 1 there. Okay? Now that I can even do more with, because again, remember the natural log and e to the x are inverse functions. They're inverses of each other. So when I take the natural log of e to the x, those cancel out, and the exponent is all that I'm left with. So f of x is actually just equal to the natural log of 4 plus x minus the natural log of x squared plus 1. And at this step, I can now take a derivative, and it'll be a lot easier than it would have been otherwise. What is f prime of x? Well, the natural log of 4 is a constant. Yeah, I don't know exactly what it's equal to without plugging it into a calculator, but I do know that it's a constant. So its derivative is 0. It just goes away. X, the derivative of that would just be 1 minus, now I have the natural log of x squared plus 1. I still need to apply the chain rule, but the function on the inside is way simpler than it could have been. In particular, we have that special case of the chain rule, the generalized natural logarithm rule, I think is what we called it. And if you remember, that was just, it turned into a quotient where the function on the inside here ends up in the denominator, and the derivative of that function, which is 2x, ends up in my numerator. And that is my derivative. Now, if I had gone through the steps of that I had mentioned before, instead of algebraically simplifying this, if I had chosen instead to use the chain rule in conjunction with the quotient rule, I would have gotten a function that might have looked different than this, but would technically be equivalent to it, in the sense that the two functions can be combined in such a way that they're shown to be equal to each other. But this process, even though it took a couple of steps, none of these steps were difficult. These were just basic applications of those log properties. So that was actually not too bad. Let's try the third example. F of x equals 5 to the power of x squared times log base 2 of x. So in this case, there's not really an algebraic manipulation that I could do to this that's going to make it easier. Instead, I'm just going to take the more direct route. So again, I do need to use the chain rule because I have an exponential function, 5 to a power, but the power is a more complicated function than just x. So I'm thinking of that as the inside function. So when I take the derivative now, remember when you take the derivative of just say 5 to the power of x, its derivative is almost itself. You get a 5 to the power of x in the derivative, but then you have to multiply that by a constant, specifically the natural log of your base, which was 5. So I'm going to get the natural log of 5 times the original function, just like you see with the log base 2 of x, just like what you see with the exponential function rule, whatever we called that. But then because I'm using the chain rule in the broader scheme of things here, I also need to multiply this by the derivative of that exponent up there. Well, that exponent looks like a product of two functions. It's x squared times log base 2 of x. So I would have to use the product rule there. Okay, let's start with the derivative of the first function. 2x is what that would look like, times log base 2 of x, plus, I leave the x squared alone, but I multiply by the derivative of this second function. So remember, the derivative of that second function is going to look like 1 over x times the natural log of that base. Or you could put the natural log of 2 here. It would look like 1 over that. But don't forget, I'm multiplying by that x squared because, again, this is part of a product rule. And that can just go right up into the numerator there. Okay? Now, this looks messy. And there's a couple of things I could do to simplify it if I wanted. For example, I could factor an x out from each one of these. That doesn't feel all that necessary to me, so I'm fine leaving my answer as is, okay? Now notice, if we had if I had done this example when we first learned about the chain rule and the product rule and all of those things, I would have spent more time writing more steps out. I would have probably identified, for the product rule, for example, what is U and what is V? So then I could write it as U prime V plus V prime U. Those additional steps are intended to be temporary. You're not supposed to be writing all of that out all the time. It's helpful when you're first learning this, but because derivatives are usually just a step in a much larger problem, like the optimization problems you'll see in the parent class this week, we don't want to spend a ton of time just evaluating derivatives. You want to get to a point where you can actually do this in one step and just think through the steps as you do them. Okay, so that's kind of why, another reason why we're spending more time this week in the support course, just working on practicing these. Okay, here's my last example. F of x equals e to the 4x minus e to the x plus 1, all quantity squared, over e to the 8x. Okay, now I could take the derivative of this directly from the very beginning using the quotient rule, with the chain rule included because I have a function inside a function here. But there is an algebraic manipulation that I could do to this, which will actually save me a little bit of time. Notice, first of all, that this is the same thing as e to the 4x minus e to the x plus 1 squared, so the numerator is not changing. But I'm squaring something in my numerator. I would like to think of my denominator also as something squared. And I could write it as e to the 4x squared. That's the same thing as e to the 8x, right? Now that I have something squared in my numerator and something squared in my denominator, I can write it as this entire thing squared. I didn't need to put that all the way over there. E to the 4x. Sorry, that got a little bit messy. That's an exponent property. I can use that, right? Ignore this stuff. This is just me being sloppy. But I can go one step further, and I could divide each term in my numerator by that e to the 4x to simplify it a little bit. E to the 4x over e to the 4x would just be 1. Negative e to the x over e to the 4x. Remember, you subtract exponents when you have the same base. That would look like minus e to the negative 3x. And then 1 over e to the 4x, because it's in the denominator, could be written as e to the negative 4x. And then that whole thing is squared. Notice I haven't done any derivatives yet, but by simplifying this function down, I'm no longer dealing with both a chain rule and a quotient rule. I'm now only dealing with a chain rule. So I've given myself a little bit of an easier time when it comes to the derivative part of this. So when taking the derivative, I need to use the generalized power rule, which, remember, is just the chain rule but applied to that specific special case. The 2 will come down. The original function stays put, 1 minus e to the negative 3x plus e to the negative 4x. My exponent I've decreased by 1, so it's to the first power, but we generally don't write the 1 when it's to the first power. And then I multiply that by the derivative of the function on the inside here. So the derivative of 1 is 0, it goes away. From our generalized exponential rule, if I have e to the negative 3x, its derivative is just negative 3 e to the negative 3x. But there's already a negative out there, so that will actually make it a positive 3 e to the negative 3x. And then here, similarly, a negative 4 will come out. I had a plus there before, so it's going to actually be negative this time. Minus 4e to the negative 4x. Okay? And that is exactly how I would want to leave that. And just as a reminder, I've mentioned this before, but typically if you do a derivative and it comes out like a product, that's the way you wouldn't want to leave it. It's not a good idea to multiply all of this stuff out because, again, remember, for one thing, that's a lot of algebra. But for another thing, what we're doing with these derivatives a lot is setting them equal to 0 and solving. And if it's already factored like this, if it's set equal to 0, it's way easier to solve using your zero product property. So multiplying this out is actually making your life harder if this is used in a different problem. Okay, that's going to be all the examples we run through this week.